All right, let's go. Differential equations with growth and decay. Okay, so these differential equations take the form of the rate of change with respect to something is proportional to itself. So how do these grow? Let's model a function for y in this case. So we have dy dt here, and we're going to try and get all of our y terms on the same side. So we have dy over y is equal to k dt, k dt. And then we could simply integrate both sides to get rid of these differential terms here. And because k we know is a constant, we can just pull this out front. And so we have on the right side, we have the integral of dt, which is t. And then we multiply it by our k up front. And over here, on the left-hand side, we have the integral of 1 over y dy, which is the natural log of the absolute value of y. Because you can't have negative numbers inside the natural log, but now you can. Because when you have a 1 over x function, it's going to look something like that. And there are values here, so you have to do the natural log of the absolute value. So just remember that when you're doing these. But we have not yet solved for y here. So let's solve for y. We're going to exponentiate both sides. So we're going to do e to the power and e to the power. Because e and ln are inverses, we're left with y on the left-hand side. I don't know why I made that one capital, but I can. And so over here, we are left with e to the kt. I also forgot the plus c over here. So when you do the plus c, you have a plus c over here. And so we don't like these plus c's being in the exponent because it looks weird and it's kind of easy to screw it up if you're just like doing the math. So with exponent rules, we know that e to the kt plus c is going to be equal to e to the kt times e to the c. And so we could call this e to the c another constant term, and many people just like calling it big C. So we're just going to call this big C. And so now we have big C times e to the kt. And so when you have a differential equation in this form, where it's not 1 over, it's just directly proportional, it's going to grow as an exponential function. Alright, so we have a word problem here. The number of bacteria in a culture is growing at a rate of this per unit time. So that's just like seconds, hours, whatever. It just doesn't say a unit. The number of bacteria present at t equals 0 is 7,500. How many bacteria are present at t equals 5? Alright, so we can model the number of bacteria. We could call it B for bacteria or P for population. I'll call it P for population, but it doesn't really say with a variable, so it doesn't really matter. As long as you know what you're talking about, everything is good. So the rate is 3,000 e to the 2t over 5. So we want to solve for the population. So we have dp, we're going to move dt to the other side. So we're going to have 3000 e to the 2t over 5 dt. And now we can simply just integrate both sides. And so now we have our the integration of dp. This is originally with respect to dt, so this is just going to be our population with respect to as a function of time. And now to integrate the right-hand side. So we could do a u substitution here if we wanted it to be e to the t is actually 2/5 or whatever. But what we could do is we know it's going to be something like 3000. It's going to start with 3000 e to the 2/5 t, because the integral of e to the t is just that. So we're going to keep this, but we need to multiply, or basically divide by this. So I need to divide by 2/5 t, which is the same thing as multiplying by the reciprocal. So it's times by 5/2. And then I'll clean this up saying 5/2 of 3000 is 7500. So I don't have the random 5/2 out the back. So e to the 2t over 5. Here we could verify that with this, if we substituted in t equals 0, we would have p of 0, which is just this part right here would be e to the 0, which is just 7500. So we got this part right. We basically confirmed that this proves that this is true. So now we want p of 5. So p of 5. And so here that is just 7500. And now it's e to the 2/5 times t, but t is 5. The 5's will cancel out, so it's actually just 7500 e squared, which we want to probably estimate to a whole number of bacteria. There's only a discrete number of bacteria at a given time. You can't have half of the bacteria in this example. So we're going to shove this into our calculator and we get 55,418. Here's one where we have to solve for that C value. Suppose there is a population and it's exponential growth. So we know that it's going to follow the form of the population is going to be equal to some constant times e to another constant times the time. We know this because it's exponential growth. This is the function for exponential growth. There are 130 after the third day and 380 after the seventh day. So we can substitute these into our equation here. So we don't have very much information, but we can try and solve for it. So 130 is our population, and this is after the third day. We don't know C, we don't know K, but we do know T. This is the third day. And for sake of writing this neatly, we're going to do 3K. And then we're going to do 380 as the population on the seventh day, so C e to the 7k. So now we have two functions. We're going to work this problem like a system of equations. And so we're going to solve for c. It doesn't matter which one you do this in, but you're going to solve for c in one, and then we're going to substitute it in for the other. So if I said 130, I'll just do the top one because I wrote it first. And then to solve for c, we're going to just say c is equal to this and divide both sides by 3 to e to the 3k. So c is 130e to the 3k, or we could rewrite this as 130 times e to the negative 3k, just with properties of exponents. Now we have a function for c, and we could substitute this in to our other equation. So I'm just taking this equation right here and substituting this in for c. So we have 380, and now c, and we know that this is c. So we're going to say this is equal to, and I'll write this in yellow to indicate that this is this c. So 130 e to the negative 3k. So that is this c right here. This is that. But it's not exactly the same. We need this e to the 7k. So we're going to multiply this by e to the 7k. And we just saw how these properties of exponents work. We're going to do the exact opposite of what we did for the kind of proving it earlier. So we add these exponents. So because they have the same base, we can add the exponents. Negative 3k plus 7k. And then we're going to also, in one fell swoop, we're going to just solve for, we're going to just divide 380 by 130. So 380 divided by 130 to get our exponential on one side, and just no constants. And then we're going to add these exponents. So that's going to be 4k. To just kind of clean up some of the math here, this is the tens digits will cancel. We can divide both numbers by 10. We have 38 over 13. We can also take the natural log of both sides. So natural log of 38 over 1/3, or 38 over 13, and natural log of this. So this remains as ln of 38 over 13. And on the right-hand side, e and ln cancel, and so we just have 4k. Here we can divide both sides by 4 and type this into our calculator to get that k is approximately 2 or 0.26. 0.268. I'll go to the 3 decimal points there. And so now we know that we now know our exact k value, and we can rewrite it in this generic equation. So we have our population is equal to c. We still have not quite solved for that yet, but we know that it's going to be c e to the 0.268 times t. Now we're going to solve the equation for C. So we're just going to go back and substitute back into our 130 equation here. So 130, but this time we now know our K. So E is a constant, and then we're going to say 3 times K, which is 0.268. And then we can solve for C by just substituting into our calculator, and we get that C is about 58 cents. And so that would be our initial population.